You know, we use computers for literally everything these days, right? From just sending a text to modeling the entire universe. But have you ever stopped to think, are there limits? I mean, are there problems that a computer, no matter how ridiculously powerful it gets, could just never solve? Well, let's break that down and get to the bottom of this fundamental question. So let's just ask it straight up. Can a computer, in theory, solve any problem you throw at it? It really feels like it should, doesn't it? But the answer is actually a very firm and fascinating no. And to really get why, we need to be super precise about what solving a problem even means in the first place. Exactly. Before we can even touch on what's impossible, we have to build a rock-solid definition of what is possible. So that's our mission today. We are going to build the very idea of computable from the absolute ground up, using the simplest ingredients you can possibly imagine. Think of it like this. We're going to build with computational Legos. To build anything, you need those basic bricks. And in the entire world of computation, we start with just three almost laughably simple functions. These are our fundamental building blocks. Okay, first up, we have the zero function. It is as simple as it sounds. You ask it for a number, and it just gives you back a zero. Every single time. That's it. It's our absolute, unchanging starting point. Kind of like the blank canvas we're going to build everything else on. All right, brick number two, the successor function. This is how we get moving. You give it any whole number, and it just gives you the very next one. Give it a 0, you get a 1. Give it a 1, you get a 2. With this one function, we suddenly have the ability to count. We can go from one number to the next. And finally, our third brick, the projection functions. Think of this as our picker tool. If you have a list of numbers, this function lets you point to and pick out the exact one you want. The first one, the third one, whichever. It lets us focus on a specific piece of information. And believe it or not, that's all we need. Those are our 3 Lego bricks. So having bricks is one thing, right? But you also need an instruction manual for how to snap them together. And it turns out we only need 3 rules of construction. Just 3 ways to combine our primal functions to build, well, pretty much anything that can be computed. So here they are, our 3 master tools: composition, recursion, and minimization. By using these rules on our super simple functions, we can construct things that are breathtakingly complex. Let's take a quick look at how each one works. Composition is the most straightforward one. It's really just like snapping those Lego bricks together. You take the result, the output, from one function, and you just feed it straight into the next one. It's a super simple but powerful way to chain operations together one after the other. Okay, now recursion. This is where things get really, really cool. It's kind of like those Russian nesting dolls. A function can solve a big problem by calling on a slightly smaller version of itself, and that one calls an even smaller version, and so on, until it gets down to a super simple base case that it already knows the answer to. Then the answer just unfolds all the way back up. And our third rule is minimization. This is our search tool, and it's incredibly powerful. Imagine you've got a function, and you want to know what's the very first whole number I can plug in that will make this thing spit out a 0. Well, minimization is the rule that does that search for you. It starts at 0, tries it, nope. It tries 1, nope. Tries 2, and it keeps on going until it finds that smallest number that works. Okay, so we've got 3 tiny bricks and 3 simple rules. I know, it feels really abstract, right? So let's actually build something we all know. Let's build addition. This is where you'll see the magic really start to happen. So how do we define addition using these tools? Well, with recursion, you always start with the simplest possible case. What's the easiest thing to add to a number? 0, right? So we make that our base case. We define plus x 0 to just be x. If you add 0, you get the same number back. And we're already using our tools here. To get that x back from the list x0, we're using our projection function to pick the first number. Now for the really clever part, the recursive step. If we want to calculate x plus some number, let's call it y plus 1, we define it as the result of a simpler problem, x plus y, and then we just add 1 to that result. And what does add 1 sound like? Yep, that's our successor function. See how it works? It keeps making the problem one step simpler until it hits our base case of adding 0. And that's it. We just did it. We have successfully built the entire concept of addition from scratch, using nothing more than our basic functions for picking a number and adding 1, combined with the rule of recursion. I mean, that is a huge moment. It shows how true complexity can grow from the absolute simplest of parts. Now this brings us to a really important distinction. The function for addition we just built only used two of our rules, composition and recursion. Anything built this way is called a primitive recursive function. But when you allow yourself to also use that powerful search tool, minimization, you unlock a whole new, much bigger class of functions. And those are just called recursive functions. So this is all great, right? We built this whole world of functions, but how does this get us back to our original question? What problems can a computer actually solve? Well, let's connect those dots right now. To answer a problem, we need a special kind of function that can give us a clear yes or no answer. Enter the characteristic function. For any question like, hey, is the number 5 a prime number? This function is designed to do one of two things. Output a 1 for yes or a 0 for no. It's basically a decider. And this table makes it super clear how it works. You give the function an input, let's say the number 5. If 5 is in the set we care about, bam, it spits out a 1. If we give it 12 and 12 is not in the set, it spits out a 0. It is a completely unambiguous yes or no answering machine. And here it is. This is the crucial link. We can officially say a problem is decidable or computable if and only if we can successfully build its characteristic function using our set of tools, our 3 base functions, and our 3 rules of construction. And this, right here, is the grand takeaway of all of this. The entire universe of problems that are solvable by any computer that has ever been built or ever will be built are the ones for which we can construct one of these recursive decider functions from those simple Lego bricks. If you can't build it with our tools, a computer can't solve it. Period. So, wow, what a journey, huh? We started with this huge, almost philosophical question, and we ended up building this beautiful, rigorous mathematical system from the simplest parts imaginable. We now have a formal, rock-solid definition for what it actually means for a problem to be computable. And of course, this leads us to the most exciting question of all, doesn't it? If this framework perfectly defines everything that can be computed, then what's on the other side? What do those problems look like? The ones for which no such function can ever be built? Well, that is a whole other story for another time.